So coming to the simulation part, I'm trying to simulate it using the CADFICO 6.1. I'm trying to open the exe file of CADFICO 6.1. So this is your CADFICO 6.1 opening window, and in that first you need to select the create model. Okay, and this is how your workspace would be, and this is our workspace. And the first step we need to do here is in which units we are going to input the dimensions. Okay, that we need to fix. So for that, here we have input, we call it as model unit. Just click that. In that you have the units like millimeter, centimeter, meter. In what units you're going to give the input, that first you need to decide. So I'm selecting here this as the centimeter. So whatever dimension I give here, the software will take it as in the centimeters. Okay, so click OK. So now I have set the input dimensions units. So next, as I told you already, we need to create the structure. First, we are trying to simulate the half-wave dipole antenna. Okay, for that I need to create the half-wave dipole antenna. I already know the dimensions as we discussed. We are going to build a half-wave dipole antenna for Suryan FM application, which is 93.5 megahertz. Lambda is 3.20 meters and lambda by 2 is 1.604 meters. Since I'm inputting in centimeters, everything would be converted into centimeters. So your lambda by 2 would be equal to approximately 160.4 centimeters. Okay. So I'm creating a line first. Okay, I'm creating a line first. So this is the window. This window will pop up when you click the line thing. So here you have you can see UVN and UVN. Okay, this UVN simply XYZ. Okay, X is here, you can see X is nothing but U, Y is nothing but V, and Z is nothing but N. Okay, so now what I'm trying to do is I'm trying to create a I need to consider a conductor, right? For building a half-wave dipole antenna, first I need to consider a conductor of length lambda by 2. So lambda by 2 length is around 160.4 centimeters. So I'm going to consider a straight conductor which is placed exactly in the Z axis. Okay, so here I'm putting the N value as 80.2. Okay, 80.2, and here I'm clearing all these things because I'm going to place the conductor exactly in the Z axis. So this would be equal to the start point of my line. So I'm creating a line. Line has 2 points, start point and end point. The start point is plus 80.2 in the Z axis, and the end point is minus 80.2 in the same Z axis. Okay, so if you click create, you can see now you can see one yellow line, right? That is our created line. Okay, the yellow line, and now the yellow line is of length 160.4 centimeters. That is from the reference. So this is our starting reference. Above the reference it is 80.2, and below the reference it is 80.2. So totally you have 160.4 centimeters. Okay, now we have created that. Then the next step is, as I told you, for this we need to apply the signal. We need to excite this antenna. For that we need to attach a port. Okay, how to attach the port? In the sense, you need to click the wire here. Okay, right click the wire, and you get an option like create port. Okay, go to the create port, and what port you are going to attach it here? I'm going to attach a wire port here. So select wire port. Okay, then after clicking the wired port, it will ask where to attach this wired port, at the start or middle or at the end. Start means here, middle means here, end means here. Since this is a half-wave dipole antenna, we need to attach the port at the middle. We need to excite the half-wave dipole antenna at the middle. So click middle or select middle, then click add. Okay, you can see the port is attached here now. So you can see the three different colors attached here. That is the port. Okay, so that's all. Now we have created the structure in the sense we have created we have taken a line and we have attached a port at the middle. Then after that we need to attach a voltage source. We need to apply the signal, right? For that we need to attach a voltage source. So for that you need to go to the port. Okay, now one port is attached. Here you need to attach voltage source to the port. Okay, so magnitude is 1. Take the default values and click add. Okay, add. So you can see the voltage source is attached to the port. Now a voltage source is also created. So close it. So now everything is ready. Okay, I have taken a conductor. In the middle I have I have attached a port. To the port I have attached a voltage source. Now everything is ready. The antenna is attached with the exciting source. Okay, so as I told you, now I need to create the boundaries. Okay, the third step is creating the boundaries. For that, go here. Okay, go to the request. Okay, in the request you have near field. Okay, just click the near field, then just simply click the create. After clicking the near field, you get this window. We are working in Cartesian coordinate system. Other things are default values. Leave the default values and click the create. Okay, so you can see a small round comes here. I mean came here. That is your near field region. Okay, that is your near field region. Then you click the far field here. Okay, far field here and 3D pattern. Okay, when you click the far field, you get a window like this, and in that you click the 3D pattern. Okay, so now you can see a boundary is created, right? So within the boundary only we are going to test the antenna. Okay, so then after clicking the 3D pattern, just click the create. So now the boundary is also created. Next, what is the next step? The next step is assigning the frequency. Okay, so what is the frequency with which we are going to test this antenna? That we need to set here. Whether we are going to test this antenna for a single frequency. We actually designed this antenna for 93.5 megahertz. Okay, we can give the input that frequency itself. Okay, 93.5 megahertz. Okay, so megahertz, how should I input megahertz here is for normally how we write 93.5 megahertz, 93.5 into 10 power 6, right? So instead of 10 you need to put e, small e. Okay, e then 6. Okay, if you input like this, then the software will take this as 93.5 megahertz. Okay, so instead of 10 you need to put e here. So in this way the software is built. So we need to follow the same thing. Okay, so now I have inputted the frequency as 93.5 megahertz. And if you don't want this, if you want to test the antenna for a band of frequencies, you don't want to test the antenna for single frequency. If you want to test the antenna for a band of frequency, then you need to select the second option. Okay, the continuous. Okay, if you select the continuous range, then you get 2 tabs to input the frequency. So in the first tab you can input your starting frequency. So we very well know the antenna is designed for 93.5 megahertz. You don't want to test the antenna for a single frequency. You want to test the antenna for a band of frequency. In the sense, you can start from like 85. Okay, 85 e power 6. Okay, 85 e6 to 95 e6. Okay, 95 e6. If you input the frequency like this, then you can see here. Okay, you can see here the frequency range in 85. So from 85 megahertz to 95 megahertz, for all these frequencies, this antenna will be tested. Okay, here in this simulation, your antenna will be tested for all these frequencies which lies in this range, 85 to 95 megahertz. So in which frequency you get the maximum radiation? Obviously, it is 93.5 megahertz, because that is our design frequency. So among these frequencies, your antenna would radiate efficiently, okay, with maximum efficiency. It radiates in 93.5 megahertz. So when we analyze the results, you come to know that. Okay, so this is how you need to input the frequency. The next thing is meshing. Okay, I told you the purpose of meshing. So how to do the mesh? Go to the tab and click the mesh tab, then create mesh. Okay, in that everything would be default value, and it will ask one parameter like wire segment radius. Okay, so what is this in the sense? The conductor diameter. Okay, the conductor, what conductor we are going to take, and what is the radius or diameter of the conductor. Here we need to input the radius of the conductor. Okay, so normally the wires or the conductor what we use for the construction of antennas, it would have the radius of 2 millimeter. So here I have I'm going to input 2 millimeter. Since all the inputs I'm feeding here in centimeter, 2 millimeter I can input it as 0.2. Okay, 0.2 centimeter is 2 millimeter, right? So I can input your 0.2 I am inputting here. 0.2 centimeter is nothing but 2 millimeter. So now I inputted the wire segment radius as 2 millimeter. Then if you click the mesh, then your antenna would be meshed. Okay, if you want to see the meshing, you can, if you zoom in, okay, if you zoom in, you can able to see your total structure is divided into parts. Okay, so see here. Okay, here it is divided, here it is divided, and here it is divided, here it is divided. So your entire part is divided into small structures, and it would be evaluated. Okay, the field analysis would be done for each and every small part. Then it would be integrated to get the final result. Okay, so now the meshing is also over. Then the next step, what I need to do is solve and run. Okay, go to the tab and click the solve and run, and click the FICO solver. So it will ask for it will ask you to save the file. So save a file in a folder. I'm creating a folder in a desktop. Okay, I'm naming it as half-wave dipole. Half-wave dipole. Half-wave dipole. And in that I'm saying I'm saving the file with the name 1. Okay, simply I'm saving the file with the name 1. Okay, so the simulation is started. You can see the simulation is running, and yes, now the simulation is completed. Okay, and you click the OK button. Okay, now the simulation is over. Okay, where you can see the result of this simulation, in the sense you need to click the post FICO. Here you can see post FICO, right? To see the result, you need to click this post FICO. So in this post FICO, you can see the structure what you created. Okay, so the wait for 1 minute. Okay, so the structure what you created, you can see the structure here. This is your port, and how this antenna radiates. This is your half-wave dipole antenna. It is a simple wire or a conductor which is placed horizontally. How this antenna radiates, okay, for your frequency, for your inputted frequency, that we can see now. Okay, so for that, in order to see the 3-dimensional radiation pattern, you click the far field here. Okay, far field, and select the far field inside. So now you can see the 3D radiation pattern. Okay, your antenna is at the center. Okay, this black line, right? The black line at the center of this donut shaped pattern, that is your antenna. From the antenna, the radiation is coming like this. Okay, so this is how your half-wave dipole antenna radiates. So this is an omnidirectional pattern. You can see your radiation pattern is, your radiation is in all direction. Okay, in one plane it is in all direction, and in another plane it is not even in all direction. So that is a definition for omnidirectional pattern, right? What is the definition for omnidirectional pattern? Your radiation should be even in one plane and it should not be even in another plane. You know what is the difference between isotropic pattern and omnidirectional pattern. Isotropic pattern, in the sense, in both the planes your radiation pattern should be even, so you get a perfect sphere. Okay, for isotropic pattern you get the perfect sphere. So if you ask me whether we get isotropic pattern out of an antenna, no, it is not practically possible. It is hypothetical. From point source, okay, if you take a point source and if you excite the point source with an RF signal, then only you get isotropic pattern. So practically the isotropic pattern is not at all possible. Only you can get omnidirectional pattern. So this is your omnidirectional pattern. In one plane you get radiation in all direction. Okay, so if you take the horizontal plane, you are getting radiation in all the directions, right? Evenly in all the direction. In all 360 degree you are getting radiation. If you take the vertical plane, so this is your vertical plane and this is your horizontal plane. In horizontal plane you are getting radiation in 360 degree, total 360 degree. But in vertical plane you are not getting radiation in all the degrees. In all the direction you are not getting radiation. Here if you see, you have no radiation, and here in this position you get maximum radiation, and here again you are getting zero radiation. So this is your omnidirectional pattern. And the gain, what you are getting here is okay, wait, we will see. Okay, so the gain, what you're getting here is the maximum gain is 1.75 is the gain. So you know what is the relation between your gain and directivity, G equal to K into D, that and all you know. Your gain is directly proportional to the directivity. If for a lossless antenna, your efficiency is 1, that is 100%. So G equal to K into D, where G is the gain and K is the efficiency and D is the directivity. For lossless antenna, efficiency, if it is 1, your G is equal to D. So directivity is equal to gain for a lossless antenna. So in that case, your directivity and gain both are same, and your gain is simply 1.75. This you would have studied in your theory also, right? The directivity of a half-wave dipole antenna is 1.75. Okay, and the directivity of a Hertzian dipole is 1.5. All these things you would have studied in your theory, right? So that's all. Now we have created the structure, we have inputted the dimension, we have created the structure, and we have simulated for a band of frequency. Then we have obtained the radiation pattern of the antenna. Okay, then if you want to do the polar plot of this 3D structure, then you can click the polar plot. Okay, then if you click the far field, first you need to click the polar plot, then far field. You are going to plot the far field radiations in a 2D plot. Okay, that is your polar plot. You can see, okay, you can see this is your E-plane cut or H-plane cut. This is your E-plane cut. Okay, this is your E-plane cut. And if you see the theta warped, you get this is your inverted H shape pattern, right? This is your E-plane cut. So what is this? How can you interpret this in the sense? Normally drawing the whenever we try to study the radiation pattern. Actually, the radiation pattern of an antenna, whatever antenna you consider, the radiation pattern or the radiation from an antenna would be in 3D. Okay, so this is how an antenna radiates in three-dimensional way only. The antenna radiates. So drawing this 3D radiation pattern is quite difficult, right? If you want to draw the radiation pattern of an antenna, if you're trying to draw the radiation pattern of an antenna, drawing this 3D pattern is quite complex, right? So for our convenience, we try to draw this in 2D. Okay, we are trying to draw the same 3D pattern in 2D by doing two cuts. One is E cut and another is H cut. Okay, how to do the E cut in the sense, here the electric field lines, so out of the antenna the electric field lines are going in this way. So these are the electric field lines, which is vertically, the vertical lines here are the electric field lines, and horizontal lines, okay, horizontal lines here are the H field lines. Okay, E field lines and H field lines are perpendicular to each other. E field lines are going vertically, H field lines are going horizontally. If we do a cut parallel to E field line, then that is called as E cut. So that if we cut this pattern parallel to E field, then we get an H shape, right? Okay, that only we are trying to plot it in the polar chart. If you try to plot the 3D pattern in 2D by doing cuts, that too by doing E cut, then you get a shape like this. Then if you select theta warped, then you get inverted H shape pattern for your E cut. Similarly for H cut, you need to select phi. Okay, if you select phi, you get the H plane pattern for your half-wave dipole antenna. So now we have simulated the antenna. We have obtained the three-dimensional radiation pattern as well as two-dimensional radiation pattern. So this is what normally they gave in your textbooks and all. These patterns. Okay, for H plane it would be circle, and for E plane it would be figure of 8, right? Inverted figure of 8 pattern you get. Okay, so these are the radiation patterns. And so as we already discussed, now we are trying to simulate a directional antenna. Okay, so in order to increase the directivity, we need to go for an array structure. So your Yagi-Uda antenna is an array antenna. We're going to use array of dipoles. Okay, previously we simulated a single dipole, half-wave dipole. Now we're going to stack more number of dipoles, and we're going to form an array structure, and the directivity will also be increased. You are going to see that, and we'll see. Okay, so this is our design. In the previously itself, we so this is our operating frequency, and the lambda corresponding to the operating frequency is 3.20 meters. And we very well know in Yagi-Uda antenna we have three different elements: reflector, driven element, and director. So the formulas and all I have clearly told prior itself. So first we need to create the reflector. So the reflector, so I'll take black color. Okay, so this is our reflector. Okay, so the reflector total length is 1.792 meters. So if this is my center, so this is my center axis. So above the reference, it should be 0.896. Okay, it should be 0.896 meters, 0.896 meters, and below the reference it should be again 0.896 meters. Okay, so totally this should be equal to wait, so totally the length should be equal to 1.792 meters. Okay, 1.792 meters. So this is our reflector. So this is our reflector, and next the driven element. So the driven element spacing I have not mentioned here. So I'll mention the spacing also. Okay. Spacing between the reflector and driven element spacing. Okay, driven element spacing is equal to 0.35 lambda, right? 0.35 lambda, which is 0.35 into lambda, which is equal to 1.12 meters. 1.12 meters. Okay. So, and similarly, the spacing between driven element and director. Driven element and director spacing is equal to this is not, actually I made a mistake here. It is correct only. So the spacing between driven element and director is 0.125 lambda. 0.125 star lambda, which is equal to 0.4 meters. 0.4 meters. So this also included, and reflector we have constructed. Then with the spacing of 1.12 meters. Okay, with the spacing of 1.12 meters, I need to build another dipole. Okay, so this is my driven element, and the driven element size would be 1.6 meter. Total size is 1.6 meter. So here I should have 0.8 meter. 0.8 meter. Below I should have 0.8 meter. Okay, 0.8 meters. That's all. So similarly, director I need to construct with the spacing of 0.4 meter. Okay, with the spacing of 0.4 meter. So this spacing should be 0.4 meter. So this spacing should be 0.4 meter, and director length is 1.44 meter. So above it should be 0.72 meter. Above it should be 0.72 meter. Below it should be 0.72 meter. So now I know all the dimensions, right? Reflector, this is your driven element, this is your driven element, and this is your director. Okay, now I know all three elements, length, spacing, everything I know. Now I can go for the simulation. So this is my design, and now I go to CADFICO 6.1, and I'm opening the exe file. So as usual, we have click this create model. Okay, create a new model. So this is our workspace. Now I need to create the structure. Okay, by inputting the dimensions, I need to create the structure. First, as usual, you click this model unit. Then in the previous design, we have taken the centimeter as our units. Now I'm taking meter as my units. So all my design, okay, all my dimensions I have taken here in meters. So I'm directly inputting my dimensions in meters. So I have selected meters and I clicked OK. Then, as usual, first we try to create the driven element. Okay, we try to create the driven element. So driven element is 0.8 above and 0.8 below. Okay, so I'm taking a line. Okay, I'm taking a line, and so my driven element is going to I'm going to place a driven element exactly along the z-axis. Okay, so this is 0.8, this is 0.8, and this is minus 0.8, and all other should be 0. Then only it will align to the z-axis. So now you can see one line is formed in the z-axis. Create. Okay, so you can now clearly see the yellow thing is what we created now. Okay, the driven element of length 1.6 meters. So the next thing is your we try to find create the reflector. The reflector should be left side of your driven element, right? Okay, so how to place the reflector here? In the sense, you can see now the driven element is exactly placed in the z-axis. I'm going to place the reflector this side and director this side. So I'm going to place the reflector in minus y and director in plus y. Then all these three would be vertically placed in the y-axis, right? So in y-axis, your all three elements are placed. Okay, so I'm going to place the reflector in the left side of your driven element. So again, I'm going to create a line. What is the reflector length? It is 1.72792 meters. So the half length is 0.896. We can refer our, so it is 0.896 and 0.896 meters. Okay, so here it is 0.896 meters, and here it is 0.896 meters minus. So it should be minus. So your okay, we give here, we get an error, then we change that. So what about your y? It should be shifted in the minus y-axis, right? So it should be equal to your point. We can see the dimension. Okay, it should be from the driven element, the reflector should be spaced in what dimension? 1.12 meters, right? So we need to put here it as minus 1.12 meters. Okay, here also minus 1.12 meters. Okay, okay, then you can here also it is minus. Okay, okay, so now you can see a line is formed here. So this is your driven element. In minus y, you have created the reflector of spacing minus 1.12 meter. So click create. Now the reflector is also created. Okay, so driven element created, reflector created. Then we need to go for the third line, which is your director. Director spacing is 0.4 meters in positive side, positive y-axis, and 0.72 meters above and 0.72 meters below. So 0.72 and 0.72, so minus 0.72. Okay, minus 0.72. Then your spacing is 0.4. Okay, plus 0.4, and this is also 0.4. No x-axis, so x-axis is 0, x-axis is 0. So you can see one more line is created in the positive y-axis. So this is your director. Okay, create. So now I have created the structure: reflector, driven element, and director. Okay, all these three are aligned vertically in the y-axis. Okay, so we very well know we need to excite the driven element. Okay, we need to attach the port, and we need to apply the voltage source to the driven element, and we need to excite that and all as usual. in the same manner as like what we have done in our half-wave dipole. We are repeating the same procedure here also. So line 1 is your driven element. So I'm selecting line 1. Then go to this wire, and we need to attach the port, right? So right click here. If you right click here, you get create port. I'm adding a wire port. Okay, wire port in the middle. Okay, add. Okay, I have added the port here. Then go to the port, right click the port, attach a voltage source, then click add, then close. Okay, I have added a voltage source also, and a frequency. Okay, I need to assign the frequency. Previously in our half-wave dipole, we have set a continuous frequency. Now I'm going to use single frequency, 93.5 e power 6, E6. So this is my frequency. Okay, so this frequency is set. Then request near field and far field. The boundary I need to create, right? Near field I have created, then far field 3D pattern created. So the boundary is set now. Okay, you can see the boundary now. And meshing. Okay, I need to do the meshing. Okay, so the wire radius is 2 millimeter. So you need to be very careful by inputting this radius here. Actual wire radius is 2 millimeter. But previously in half-wave dipole we inputted it in centimeter. Now the inputs will be taken in meters. So it should be 2 millimeter in meters is 0.002. Okay, is 2 millimeter. Okay, if you click mesh, so now my structure is meshed. If you zoom it and if you see you can see the partitions. So you can see here the partitions. Your structure is divided into so many parts, and it will be evaluated. The field analysis will be done. Okay, then that's all. Then we need to go for solve and run. It will ask for saving. So you can name your file as 3-element Yagi-Uda antenna. Okay, 3-element Yagi. Okay, after saving, yes, my simulation is over. Then click OK. Then go for the result analysis, where you can find the result in the sense the post FICO. So click the post FICO, you get the created structure. Okay, so see some mistake we have done here. Okay, that is why our structure is not came in the proper way. Okay, some mistake we have done. We try to correct the mistake. What is the mistake? We have done some mistake with the reflector. The reflector is not aligned properly in the y-axis. We see that. What is the mistake we have done? Okay, we go to the workspace. Then which line corresponds to the reflector? Line 2, right? So if we take line 2, see here. So this 0.5 I forgot to delete. So you need to set that also to 0 in order to for the proper alignment. So I have made it now. Then your line 2 is not meshed now. You have done some alteration in your line 2, that should be meshed. So again you need to mesh. Okay, again you need to mesh. Okay, create mesh. Then as usual, if you do meshing, your line 2 is the altered line 2 is meshed here. Okay, then you go for solve and run. Okay, you try to replace the already saved file, and now if you go for the result, I have clicked the edit FICO. Now if you go for the post FICO to see the result, yes, now we got the proper aligned 3-element Yagi-Uda antenna in the post FICO. Okay, so this is our 3-element Yagi-Uda antenna, and this is a reflector, driven element, director, and the driven element is attached with the port at the center, and it is applied with the voltage source. So how the radiation would be? Okay, from this, how the radiation would come. What is our expectation? Since this is a directional antenna, the direction should be in only one direction. Okay, it should not be omnidirectional. The direction should be in the only one direction. So how my radiation from this, that we'll see. Okay, for that you click far field and far field. So now you can see the radiation is only in the one direction. It is unidirectional. It is not bidirectional or it is not omnidirectional. The radiation is unidirectional. So along the director side, it is radiating. And if you see the gain value here, it is 4.0. Okay, so the total gain value is 4. The directivity is 4 if the antenna is lossless. We know the formula G equal to K into D. Gain equal to efficiency into directivity. If efficiency is 1, that is if the antenna is lossless, efficiency is 1, then your G is equal to D. So the directivity and gain for this structure is 4 here. Okay, so now we have simulated a 3-element Yagi antenna and we obtained the radiation pattern in 3D. So previously we have seen 3-element Yagi, right? In that we got the directivity or gain around 4, right? Now we are going to see the 4-element Yagi. Okay, we are going to increase one more director in the right side. Okay, so here if you see we have the director, one more director placed in the right side. So I have included one more line and I have meshed it. That's what I have done in the previous, that's a modification I have done in the previous design. Then I have actually simulated it, and if you open the PostFICO for this file, okay, so we'll go by step by step. Okay, so if you click the solve and run or FICO solver, you get now your simulation is done. And if you go to the PostFICO, then you get the simulated structure. Okay, so this is now you can see this is a 4-element Yagi. Okay, one reflector, one driven element, 2 directors. Okay, so I have taken the same spacing what we have used here, 0.4 meter. So here also 0.4 meters. Totally it is 0.8 meters. The second director is 0.8 meters away from the driven element. Okay, so the length is same as that of the director what we have used previously. Okay, so if you see the radiation pattern, okay, 3-dimensional radiation pattern for this structure, so again it is unidirectional. Some back radiation is there, and the maximum radiation is in one direction. That is, the radiation pattern is unidirectional. And here the important thing is, here you can see the directivity or the gain is increased. Previously it was 4, now the gain is increased to 6. Okay, that is the important thing you should note here. So if you go on increasing the directors, okay, then you can increase the directivity. So this is the other thing, this is the important thing you should note here. Okay, so if you want to plot the 2D plot for this structure, then you can use the polar plot and far field. If you select, this is your 2D plot for the obtained 3D radiation pattern, and select 90 degrees. So this is your 2D plot. And for phi, it is you can select 90 degree or 180 degree. Okay, you select 90 degree. Okay, so this is your phi cut. Okay, that is your H-plane cut. This is your H-plane cut pattern, and this is your E-plane cut pattern. Theta. So this is your theta at theta at 180 degrees. Wait, we'll select 180 degrees. Okay, so theta at 90 degrees. Yes. Okay, so this is your E cut, and this is your E cut, and if you select phi, and if you select 90 degrees, This is your H cut. Okay, both are unidirectional. So this is the other thing you should note as far as 2D plot is concerned. So now we have simulated two different antennas, right? One is omnidirectional antenna, other is directional antenna, and we have obtained the radiation pattern in three dimension as well as in two dimension. Okay. So we come to the conclusion. As of now, we have seen the design and simulation of a half-wave dipole antenna, then three-element Yagi-Uda antenna and four-element Yagi-Uda antenna. Among these three antenna, your half-wave dipole antenna is an omnidirectional antenna, and the other, okay, the Yagi-Uda antenna, three-element, both the three-element and four-element Yagi-Uda antennas are directional antennas. Okay. I hope you have understood how to use the CAD-FICO tool for antenna simulation. Once you have done the antenna simulation, after getting the appropriate results after optimization, that is after optimization, you can export the Kerber file. Option is there in the CAD-FICO tool itself. You can export the Kerber file, and by giving the Kerber file as input to the fabrication machine, in our department itself, we got the fabrication machine, PCB fabrication machine. So I'm speaking about the microstrip patch antennas. Okay, if you are trying to design and simulate and fabricate planar antennas, you can use this procedure what I'm saying now. Okay, as far as the three-element Yagi, four-element Yagi, and half-wave dipole antennas, these things and all you can do by buying the aluminum pipes and cutting it and assembling it. So as far as the planar antennas, that is the microstrip patch antennas are concerned, you can what you can do is first to try to design the microstrip patch antenna, get the dimensions, then try to simulate the same using any one of the CAD tools. Okay, other than CAD-FICO, you have ANSYS HFSS tool also. You can use that also for your simulation. Then after simulation, you need to optimize in order to get the appropriate results. So after optimization, you can export the Kerber file. Then with the Kerber file, you can fabricate the antenna. Okay, you can fabricate the planar antenna. In the PCBs, you can fabricate the planar antenna. That facility is also available in our department. You can utilize that facility and fabricate the microstrip patch antennas, planar antennas. So after fabrication, you need to validate, right? You need to test and validate, right? For that also, in our department, we got the facility, okay? Up to 16 gigahertz. If you are trying to design antennas up to 16 gigahertz, you can design it, fabricate it, and we have the network analyzer, vector network analyzer, to test it, okay? Test it and validate it. Okay, so what you can test here is you can test the impedance characteristics, that is S11, then VSWR. So these things you can test here, reflection coefficient, S11, VSWR results. You can test it here using the vector network analyzer available, and you can validate that. You can validate with your simulated output. Then for the radiation characteristics, in order to test the radiation characteristics, we need to have the chamber, okay, anechoic chamber. That is right now we don't have that facility. Our department don't have the facility. So some centers are having that. Robert Bosch in Tyagarajar Engineering College at Madurai, Tanjavur. Tanjavur Tyagarajar Engineering College, and Chennai SSN College of Engineering. They have the partial chamber facility. SSN College have the partial chamber facility. They don't have the full-fledged anechoic chamber, but they have the partial chamber. But at Tyagarajar College and at Bosch and at Samir Chennai, they have the full-fledged anechoic chamber. There you can test the radiation characteristics, and you can get the radiation pattern of the antenna, okay, fabricated antenna. So these are the things you can do. And if you want to take up your projects in antennas, you can very well take the projects related to the antenna fabrication and testing. So 90 percentage of the project you can complete here itself, that is simulation, design, simulation, fabrication and testing, impedance characteristics testing up to impedance characteristics testing you can do here itself in our department itself. That itself is enough. If you, further, if you want to test the radiation characteristics, you can go to any one of the centers as I mentioned earlier. So with this I can conclude the presentation. Thank you all.